All right, let's talk about something that's totally changing the game in car safety. Our cars are basically becoming supercomputers on wheels, right? Well, that means the old school ways of keeping us safe, they just don't cut it anymore. We need a whole new playbook, a completely unified approach. So let's get right into it.
So, I'm going to start by asking a simple question. When you think about what's dangerous in a really modern, software-driven car, what's the first thing that pops into your head? Well, the answer is a lot more complicated than you might think.
For literally decades, the main thing we worried about was a system just failing. A brake part wearing out, maybe a software bug throws an error code. This is the traditional world of what we call functional safety. But now that every car is connected to everything, we have a whole new threat. Malicious attacks from the outside. I'm talking about someone trying to grab control of your car from thousands of miles away. That's the world of cybersecurity.
And then there's this third thing, and it's a little more sneaky. What happens when the car's amazing tech, its cameras, its AI, runs into a situation it just wasn't built for or just gets confused? A blinding sun flare, a strange shadow on the pavement. It's not a failure and it's not a hack, but it's still a danger.
So here's the bottom line. These three risks, the internal failure, the external attack, and the system's own limitations, they are all tangled together. You absolutely cannot look at them in their own separate boxes anymore. The old way of thinking is officially broken.
And that brings us to the solution, what we're calling the Automotive Safety Trinity. This is a whole new way of thinking that treats these three pillars not as separate subjects, but as one single integrated thing. So let's break down each piece of this trinity one by one.
First up, we've got functional safety, or FUSA. This is all about the standard ISO 26262. The best way to think about it is like making sure the walls of a fortress are solid and they're not going to just crumble on their own. It's all about protecting you from internal problems. If a part breaks, the whole system is designed to go into a safe mode. That's fail-safe.
Next is cybersecurity, and this is covered by ISO/SAA 21434. So if FUSA is the strong fortress walls, then cybersecurity is the guards at the gate, actively looking for and stopping invaders. The goal here is to be fail-secure, which means stopping anyone from taking control who isn't supposed to have it. And the third pillar is SOTIF. It's a mouthful, safety of the intended functionality. This one handles those weird situations where nothing's actually broken and no one is hacking you, but the car is still in a risky situation because of its own built-in limits. This is like the scout up in the watchtower who spots a river that's about to flood. It's not an enemy attack, but it is for sure a danger. So here they are, the three pillars, all lined up. But, looking at them separately is kind of missing the point. The real magic, the absolute key, is how they connect. So why do we have to fuse them? Well, think about it. A cyber attack could absolutely trigger a massive functional safety failure. Or what if you try to fix a security hole by, say, adding super heavy encryption? That could slow things down just enough to miss a critical safety deadline. See? You can't touch one without affecting the others. They're totally locked together.
Okay, so how in the world do you actually pull this off? How do you merge these things together? Well, it has to start at the very, very beginning of the whole process with a totally unified way of looking at risk. The answer is a process with a pretty cool name, HATARA. It stands for Hazard and Threat Analysis and Risk Assessment. You can think of this as the central nervous system for this new safety philosophy. What it really does is force all the different teams of engineers to actually talk to each other from day one.
So HATARA basically works by mashing three different analyses together. You've got HARA for functional safety stuff, TARA looking for cybersecurity threats, and HIRE for those tricky SOTIF scenarios. But here's the crucial part. It maps them all together. So if the security team finds a tiny software hole that could, in theory, cause the car to suddenly accelerate, a super high-risk functional hazard, that little software hole instantly becomes a top priority for everybody. Okay, so you've looked at all the risks together. Now what? Now we get to the fun part, the design phase. Let's see how this unified thinking actually shapes the hardware and software that goes into the car. Here is a perfect textbook example of a conflict you'd run into. The cybersecurity team, rightly, wants to encrypt every critical message to make sure it's authentic. But the functional safety team knows that their system has to act on a message in under 10 milliseconds. That's the fault-tolerant time interval, the FTTI. And heavy encryption can add time.
can add latency, which could be the difference between safety and disaster. So this unified process doesn't look for a compromise. It looks for a solution. The conflict gets flagged early on by HATARA. So what do the architects do? They design in a specific piece of hardware, a hardware security module, or HSM, that has one job and one job only. Do all the complex math for encryption really, really fast. And the result? You get both. You get rock-solid secure communication that still meets that strict sub-10 millisecond safety window. It's a win-win. So designing a tough system is one part of the puzzle, but proving that it's actually safe? Well, that requires an equally fused and combined approach to testing. You have to basically try to break it from every possible angle all at the same time.
And what that means is your test setup has to be incredibly advanced. It can't just check for one kind of problem at a time. No way. It has to be able to, say, inject a fake hardware fault while at the same time running a full-on hacking attempt while also simulating a freak blizzard all at once.
Let's make that more real. Here's a combined test case for you. A simulated hacker sends a fake command telling the electric motor to spin up. That's the cyber attack. The test is designed to answer one question. Does the functional safety system see this weird, unexpected command and correctly cut the power? That's how you prove your fortress can actually withstand a real-world, combined assault. And this all leads us to one final and honestly hugely important point. In this age of connected cars, safety is not a one-and-done thing you achieve at the factory. It's a living, breathing, continuous process that has to last for the entire life of the vehicle on the road. So what does that look like? It means you have a security operations center watching the entire fleet of cars 24/7 for new threats. It means the cars themselves are constantly sending back data about weird edge cases they run into so the SOTF models can learn and get better. And it means every single over-the-air update has to be secure to stop tampering and safe, with a backup plan to roll it back if an update goes wrong. So look, if there is one thing you take away from all this, let it be this quote. The entire new philosophy of car safety really boils down to these three things: interlocked requirements, collaborative architecture, and fused verification. You need all three working together all the time. This new trinity of safety is, without a doubt, our best shot at protecting cars that are getting insanely complex by the day. But it does leave us with one big nagging question to chew on. As our cars literally transform into rolling data centers, is the whole idea of absolute safety even possible anymore? That's something to think about.